Hi everyone, and welcome back to Spaced Out. For those of you who don't know me, my name's Dia and I'm a student at Caltech studying astrophysics and planetary science, and I love space. Today I'll be starting to introduce one of my favorite topics in astronomy, planet formation. However, this cannot be possible without star formation, which is what this episode is all about. Star formation is a fascinating blend of physics and astronomy, and hopefully this episode will help clear up some of its complicated processes. First, let's start from the beginning. Well, somewhere around there. We'd have to first start with the materials that stars form from, giant molecular clouds. These clouds are filled with gas and dust. The gases are mainly hydrogen, with some helium and heavier elements. The clouds are largely stable, with thermal pressure and gravitational forces competing to win. This thermal pressure is caused by the gas particles within the cloud constantly moving and colliding with each other. These collisions generate what is called thermal pressure. Gravity, of course, is pushing the cloud to collapse, while thermal pressure is pushing the cloud to expand outwards. You can kind of think of this idea of competing forces similar to what happens when you push a ball underwater. There can be many forces at play here depending on the scenario, but the two main ones are applied force, coming from you pushing the ball underwater, and buoyant force, which is the water resisting to this pressure and pushing the ball back up. If you win, the ball stays down underwater. But if buoyant force wins, it'll come up and hit you right in the face. Similar to that, gravity and thermal pressure are at play in the case of a star forming. For a cloud to be stable, these two forces are balanced and one doesn't dominate over another. However, there are external situations that can create instability in the cloud, such as collisions with other molecular clouds or even shock waves from supernova, which are the death of stars, happening nearby. These situations can cause regions of the cloud to exceed what is called their Jeans mass. Jeans mass is the minimum mass a cloud has to have in order to undergo gravitational collapse. If the cloud is any less massive, instead of undergoing gravitational collapse, the material in the cloud would just sort of disperse into space with nothing to really hold it together. If a region within the cloud were to exceed this critical mass, the gravitational force would increase, overwhelming the thermal pressure, and the cloud would become gravitationally unstable. In other words, the gravity would win over the thermal pressure. And since gravity is the force pushing the cloud into itself, the cloud would collapse. However, physics is still at play. During its gas cloud stage, the cloud is rotating. This rotation may not be how you generally think of, not like a spinning top. Rather, these clouds have random motions within, and may even have somewhat of a slow overall rotation. This all comes from the conservation of angular momentum. As a quick physics aside, let's discuss what angular momentum actually is. The best way to describe what angular momentum is to think of it sort of like linear momentum. Linear momentum is normally explained in physics classes purely as an equation, the product of mass and velocity. The larger an object is, and the faster it's moving, the more momentum it has. The best physical understanding of linear momentum is how hard the object is to stop. The harder it is to stop, the more momentum it has. If you could choose between having a basketball rolling at you at some speed versus a boulder rolling at you at the same speed, you would, and probably should, choose the basketball since it's easier to stop, meaning it has less linear momentum. Linear momentum essentially describes how much motion an object has while moving in a straight line. Angular momentum is just like linear momentum in that it measures how much motion something has, except it measures how much motion something has while it's rotating. Angular momentum depends on the mass, the speed of rotation, and how far the mass is from its rotating axis. A really important principle regarding angular momentum is that it's conserved. This means that if there are no external forces acting on a system, the total angular momentum for the system must stay the same. Angular momentum is written as a product of the system's moment of inertia and its rotational velocity. Moment of inertia is basically how hard it is to stop an object from spinning, or, in other words, how hard it is to get an object to spin. It depends on the mass of an object and how the mass is distributed along the axis of its rotation. Think of how easy it is to spin a pencil. It has very little mass, and all the mass is concentrated around its rotation axis. In this case, it'd be the center of the pencil. Now, imagine trying to spin a dumbbell by holding onto the middle part. This would be much harder to rotate because the mass is much more spread out. It has two large masses on either end of the rotation axis, so the dumbbell would have a higher moment of inertia than the pencil. Angular velocity, the other component of angular momentum, is basically how fast something is rotating or spinning. Now, a good example of the conservation of angular momentum is with a merry-go-round. If you're at the edge of a merry-go-round, you're further from the axis of rotation. The axis of rotation here is the center of the merry-go-round. Now, if you're further from the axis of rotation, you've increased the total moment of inertia, since the mass around the merry-go-round is spread far away from the axis of rotation. Remember, angular momentum is the product of the moment of inertia and the angular velocity. To account for this increase in moment of inertia, your angular velocity will decrease in order to keep the total angular momentum constant, meaning you would be moving slowly. However, if you move closer towards the center of the merry-go-round, you would be closer to the axis of rotation, and you'd notice that you start moving a lot faster. This is because the moment of inertia is decreasing since you're closer to the rotation axis, and in order to keep the total angular momentum constant, your angular velocity would increase. Now let's get back to astronomy. The cloud has to conserve angular momentum from when it formed and any interactions it had during its formation. This conservation of angular momentum is still at play once the cloud starts to collapse. While the cloud collapses, its size is also decreasing. In order to conserve angular momentum, the cloud's rotation must also speed up to account for the size being less spread out. This idea is classically represented with an ice skater. When ice skaters have their arms spread out while spinning, they spin a lot slower than when they pull their arms in. However, as this cloud is shrinking and spinning faster and faster, material from the rest of the cloud is still falling into the collapse. There's a bit more complicated physics that occurs here, but simply explained, as the cloud spins while collapsing, the fast rotation pushes the material outwards. This is the centrifugal force, while the gravitational force from the collapse pulls the material inwards. The center of this cloud is where the density and pressure is the highest and is where the protostar forms. The protostar is an early stage in star formation, marking when the star comes into existence as what we classically think of as a star. It emits light from the heat of accretion and collapse, but it doesn't have any nuclear fusion in its core. The surrounding material, subject to the competition between the centrifugal and gravitational force, flattens the cloud around the star, forming a disk. I should mention that the star doesn't stay as a protostar. The protostar will continue to accrete material from the disk, and the temperature and pressure in its core will keep increasing. But when the temperature reaches a critical point of around 10 million degrees Celsius, it'll begin nuclear fusion in its core. This marks the transition of a protostar to what is called a main sequence star, signified by hydrogen to helium fusing in its core. This is what powers the star and allows it to generate energy, heat, and light. Our sun is currently a main sequence star, as this stage can last from millions to billions of years depending on the star's mass. As always, thank you for listening, and talk to you next time!